Hello, Integrated Math 1. Welcome to lesson 2.1.2a. We're on day 1. And since we are on day 1, we are on page M2-23. We're just going to kick it off with some warm-ups here. Kind of picking up a little bit where we left last time, but we're going to dig a little deeper today. So first of all, I want you to determine the slope of the line between each pair of points. And if you recall last time, we talked last time about for slope, you're going to subtract your y coordinates on top, subtract your x coordinates on the bottom. So go ahead, hit pause, find the slope for between each of these points, and then go ahead and hit play when you're ready to check your work. So I'm going to use my slope formula, and I can see here that my y coordinates, got my little pen here, there we go. I can see that my y coordinates, this is my y1 and my y2. So my y coordinates are 12 and 10. So I'm going to do 12 minus 10 on top. And I can see my x coordinates here as well. So I'm going to do 3 minus 0 on the bottom. So on top, I'm subtracting my y coordinates, 12 minus 10. And then on the bottom, I'm going to subtract my x coordinates, 3 minus 0. So if we do that, it's not that bad. 12 minus 10 is, of course, 2. And 3 minus 0 is 3. So it turns out my slope is 2/3. Yay. Don't freak out over decimals. They want to be treated just like all the other numbers. So again, I'm going to call this x1 and y1. Again, I'm going to call this x2 and y2. Oh my gosh, because that's my second x coordinate. So fine, I will subtract my y coordinates on top, negative 4.5 minus 4.5 on top, and 1 minus a negative 1 on the bottom. Negative 4.5 minus 4.5, that means they go together, right? Yeah, that's a negative 9, isn't it? And of course on the bottom, 1 minus a negative 1, well, you guys know, I'm going to use another color here to make it a little easier to see. You guys know that double negatives become a positive, so 1 plus 1 is of course 2. So I have negative 9 over 2. Yay, is my new slope. And last but not least, for number 3, again, let me go back to my red color. Again, this is my first x and my first y, my second x and my second y. So I'll subtract the y's on top, just like the formula, 12 minus 0. I'll subtract my x's on the bottom, 0 minus a negative 1. 12 minus 0 is pretty easy. We know 12 minus 0 is 12. And of course, minus a negative makes that a plus. 0 plus 1 is 1. So I have 12 over 1, which does simplify down. I can take that further. 12 over 1 is actually just, well, 12. If you left it as 12 over 1, that would have been okay as well. So we found our slope for all of these. Yay, slopes. So let's have some fun with functions, yeah? What we're going to start doing today is making sense of different representations of linear functions, right? We've seen them as graphs, we've seen them as tables, we've seen them as equations. So let's start making sense of these guys. So our learning goals over the next couple of days, we're going to determine whether scenario, equation, table, or graph represents a linear function. Can we look at a scenario and say that's linear? Can we look at an equation and say that's linear? Can you look at a table and say that's linear? Can you look at a graph and say that's linear? That's going to be one of our big goals today. We are also, of course, are going to continue calculating the average rate of change from a table. Please remember, average rate of change is code for slow. Just like we did on the warm-up, we're going to be doing that with tables. And we're actually going to dig a little deeper. We're going to write functions given a table of values. If you have a table and you're like, hey, that's linear, can you write a function from it? Because I think you can. And next up, interpret expressions that represent different quantities in terms of a context and a graph. So yes, we have this graph, that's great. We have an equation, that's great. But what does it mean in this particular situation, in this particular scenario? And of course, we'll be comparing different equation representations of linear functions. So we'll just compare our different representations, see if they make sense. So our key terms as we go throughout all of this, we've got polynomial, degree, leading coefficient, 0 of a function, that's a big one. And these will be our key terms over the next few days. So you know how to determine whether a relationship represents a linear function. And you know how to write an equation for the function, right? Those arithmetic sequences, we have that down, and we know how to turn them into function notation now. So how can you use the structure of the equation to identify characteristics of the function, right? Right. It all goes back to those arithmetic sequences. It all goes back to that whole constant difference, right? Common difference. That is our slope. That's what you're going to be looking for. So to get things started, we're on page M2-24. Determine whether each representation models a linear or a non-linear function. Be sure to explain your reasoning. So I've got 3 scenarios here, scenario A, B, and C. We also have some equations. We also have some graphs. I can only fit so much on my page at a time. For every single one of these, can you go through and decide whether or not it's linear? And make sure you can tell me why. Go ahead and hit pause to go through all of these on page 24, and then hit play when you're ready to check your work. So the scenarios are probably the most difficult ones. So we're going to start off with the scenarios. Scenario A, a tree grows 3.5 inches each year. So I'm like, all right, well, so that means I'm adding 3.5 every year. That feels pretty linear to me, right? That feels linear. In fact, here, I'm going to erase that because that's going to be in the way. So I'm adding 3.5 inches every year. If it's adding every year, that feels like an arithmetic sequence. That feels like a linear function. Absolutely. All right. Scenario B, the strength of our medication decreases by 50% each hour it's in the patient's system. This means it's getting cut in half every hour, right? So every hour we lose a half, we lose a half. So if I'm dividing by 2, or maybe you could even think of it as multiply by a half, right? It keeps getting cut in half. That's not an arithmetic sequence. That's a geometric sequence, isn't it? So that's not linear. That's not linear. Geometric sequences are not linear. We know this. We know this. Scenario C, the area of a square depends on its side length. You guys know that. You find the area of a square by multiplying side times side. So if the area of a square is, I'm going to say my side squared, side times side, because I'm running out of space to write side times side, so I'm going to write side squared. Wait a minute. I'm multiplying the side times itself. The very fact that I'm multiplying says that's not arithmetic sequence. That's not a linear function. Fine. All right. What about your equations? How'd you do on these? Was it a linear function or a nonlinear function? Well, I rewrote a few of these just to help my brain out a little bit. I was like, I think that's linear, but I like to have the x out front. So you know what I did? I just real quick, I was like, all right, I want my negative 9x to be in front, and that's a positive 14, right? So I'm going to put a little like plus 14. Hey, that's a linear function. Y equals mx plus b. Psh, totally a linear function. I'm looking at equation B, y equals 2 to the x power plus 1. Wait a minute. There's an exponent. The moment I see an exponent, especially an x in the exponent, whoo, that is not a linear function. In fact, I think that's an exponential one, isn't it? Yeah. Equation C. You know, equation C, I had a little rough time because I was like, well, it's not exponential, but I don't like the form. So you know what? I kind of did a little bit of work here. 1/4 times x is, I did some distribution, so it's 1/4 x. 1/4 times 7 is 7/4. And I do want to combine my like terms, so maybe instead of 1, I could rewrite that as 4/4, right? Because 4 divided by 4 is 1. So I'm going to put minus 4/4. And now I have y equals 1/4 x, 7/4 minus 4/4 is 3/4. Huh. You know, there's a bunch of fractions there, but that's got the y equals mx plus b going on, doesn't it? It does. That's a linear function. It looked weird. It looked weird. But it's a linear function. Yeah. Okay, okay. What about these? What about these? What about these? So one messed with me because I was like, wait, the X isn't even changing. Check it out. One could be 3, one could be 4, one could be 5. Guys, my input has more than one output value. It's not even a function. Forget linear. It's not even a function. Oh my gosh. Not okay. All right, so A isn't even a function because my input has more than one output. Fine. Table B, well, let's see. X is going 3, 4, 5. Cool. So I'm going to check the first differences. We did that a few days ago, right? First differences. So 3, 4, 5. I'm going to check my first differences. And I'm like, okay, 1 to 1, 0. 1, 0. Well, I guess it is a constant difference. It's a constant difference of 0, but it is a linear function then. I forgot my first differences are the same. That's good. And table C, again, it does look like I can use first differences here, right? -9, -8, -7. So up 1, up 1, up 1. Awesome. I can use first differences here. So 45 to 30, it looks like we have to subtract 15. 30 to 15, it looks like I again have, oh, I got the same first differences. It's a linear function. Yay. And then for the last ones, the graphs. These were the easiest, weren't they? Yeah, the graphs were the easiest ones. Of course they were. Because you know it best be a straight line. And if it's not a straight line, it's not a linear function. So graph A, it's got a little bit of a curve. Just a little curve. Just a little curve, but enough of a curve. It's not a linear function. Graph B, ooh, look at that. That's a nice straight line. That's a linear function. Absolutely. Graph C, oh, you know, it's a nice straight line, but check it out. It's doing the whole thing. It doesn't even pass the linear, the line test, the vertical line test. It doesn't pass the vertical line test because it hits in more than one place. It's not even a function. After all that, not even a real function. All right. Let's move on. Page M2-25. Let's talk about activity 2.1. Let's interpret linear functions. So each table of values in the previous activity had consecutive input values, right? Those tables that we did, it went from 3 to 4 to 5. It was just like boop, 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 right in order. And even the other table, -9, -8, -7, it was like doop, 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 right in order. So tables that do that your X values are just like boop, 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 one right after the other, those allow you to use first differences. That can tell you, hey, it's linear, it's not linear. But often our input values are in intervals other than 1. It's not like 1, 2, 3, 4, 5. It's not going in order. And in fact, sometimes the input values are in a completely random order. So to determine whether these tables represent linear functions, we can't use first differences anymore. You need to make sure that the slope or the average rate of change is constant between all the given points. So guys, instead of first differences, you have to go back to the slope formula that we used in the warm-up. Yes, you do. So I would like you go back to that slope formula that we used in the warm-up. This guy right here, remember this lovely guy right here? Yep. And I would like you to determine whether each table represents a linear function, because here's what you now have to do. You have to find the slope between these two, use the slope formula, use the slope formula again between these guys, yeah. Use the slope formula again between these guys. You have to make sure you're getting the same slope every single time. I know it's a lot of work, but that's why we did the warm-up that we did to get you ready. So go ahead and hit pause. We've got a couple of tables here. I can only fit one table at a time on my screen, but you can see there's a couple of tables on your page. Find the slope between each set of points. Subtract your y coordinates on top. Subtract your x coordinates on the bottom. Find the slope between each set of points and make sure you're getting the same slope every single time. You may want to have a calculator handy to help you with this, just so you know. Go ahead and hit pause. find all the slopes, decide if it's a linear function, and then hit play when you're ready to check your work. So because these are not in perfect little order, right? It's not like 1, 2, 3, 4, 5. No, I've got like -2 to 1 to 4 to 7. There's all kinds of stuff happening here. I'm going to start by finding the slope between these two sets of points. So I'll subtract my y's on top, 4.75 minus 5.5. Subtract my x's on the bottom, 1 minus a -2. So when we do that, you can see all my work kind of like came out here. When we do that, 4.75 minus 5.5, I used a calculator. I got -0.75. Double negative, ooh, that becomes a positive. 1 plus 2 is 3. And then again, I use my calculator to simplify. -0.75 divided by 3 is -0.25. Now, in order to be a function, I need to keep getting this answer over and over again. Let's do the next set. So I'll subtract my y's. 4 minus 4.75, that goes on top. I'll subtract my x's. 4 minus 1, that goes on the bottom. Use my calculator. 4 minus 4.75 is -0.75. 4 minus 1 is 3. You know, we already did this. If you divide with your calculator, you get -0.25. So far, so good. But this last set also has to match. They've all got to match. If even one of them goes off, it's not a linear function. So let's do it one more time. Subtract my y's. 4 minus 3.25, or pardon me, the other way around. 3.25 minus 4, 7 minus 4. So bottom, or pardon me, top, bottom. If I do 3.75 minus 4, I get -0.75. 7 minus 4 is, of course, 3. And if we divide, we get -2.5. That's awesome. So you guys, do you know what this means? Do you know what this means? This means it's a linear function. So make a little note. Linear function. Yeah, it's a linear function. Rock on. Oh, but wait, there's more. Did you catch this? If it is a linear function, we have to write the function. Fine. We can do this. I can use, oh, look, first term. I can use my arithmetic stuff, my arithmetic tricks, right? I'm going to use my arithmetic trick, right? Only instead of A, I'm going to use F. So I'm going to be like, fine, F of X equals my first term, which is 4.75, plus my common difference. Oh, my common difference is negative. So negative 0.25. Times, instead of an n, I'm going to use x minus 1. You know what, though? I do want to clean that up. Since it is function notation, here, I'm going to erase this. Since this is function notation, I am going to go ahead and clean this up. Sorry, I'm going to bring up the pretty one in just a second. There's the pretty one. So I am going to go ahead and I'll distribute -0.25 times x is -0.25x. -0.25 times -1 is a positive 0.25. I'm going to move my -0.25x to the front. We like to have our x in front. And 4.75 plus 0.25 is 5. Yeah. How'd you do with B? Are you feeling a little overwhelmed at this point in time? Hang on, let me bring back my pen. All right. So again, let's find the slope between these two guys. 13 minus 5 on top, 2 minus 0 on the bottom. 13 minus 5 is 8. 2 minus 0 is 2. 8 divided by 2 is 4. Now, I need to keep getting 4s. So we're going to do it again for the next set. Pew, pew. So 21 minus 13 on top. 4 minus 2 on the bottom. 21 minus 13 is 8. 4 minus 2 is 2. 8 divided by 2 is 4. So far, so good. But we got to check one more time. Oh, what's happening to my screen? Camera went funky. So let's check one more time, this last one. So 29 minus 21, 8 minus 4. So 29 minus 21 is 8. 8 minus 4 is 4. Wait, 8 divided by 4 is 2. So close. So these match, but we said they all have to match to be a linear function. Guys, it's not a linear function. One of our slopes went like off. We were doing so well. Oh, well, since it's not a linear function, we're just going to say it's not a linear function then and call that done. So analyze each situation represented as a table of values. So here's Dylan. Dylan sells pretzels at festivals on weekends. The table shown is a record of his past sales. So 15 pretzels earned him $37.50. 42 pretzels got him $105. 58 pretzels got him $145, and 29 pretzels earned him $72.50. So, what does this table tell you about his sales? I would start by finding the slope. That's my advice. Go ahead and hit pause to find what this table tells you about his sales, and hit play when you're ready to check it. So I went ahead and I started off by finding the slope. I just picked any 2 points. You can pick any points you like because that's a thing. So just to keep it easy, I'm just going to pick these first 2 points right here. And I'm going to go ahead and subtract my y coordinates on top, 105 minus 37.5, subtract my x coordinates on the bottom, 42 minus 15. I totally used a calculator. 105 minus 37.5 is 67.5. 42 minus 15 is 27. And again, with my handy calculator, I did divide. 67.5 divided by 27 is 2.5. But let's talk about what this means, because we want to talk about his sales. So yay, the slope is 2.5. Huzzah. But what does that mean? Well, this is the number of pretzels he sold. This is how much money he made from selling those pretzels. Guys, Dylan earned $2.50 per pretzel. Yeah, he's earning $2.50 per pretzel. It's great. I hope they're the soft pretzels. The kind that you can like dip in like warm cheese. Probably charged extra for the cheese. I would have charged extra for the cheese. So here's my question. Now that you know that he's making $2.50 per pretzel, how much money would Dylan earn if he sold 75 pretzels? Hit pause, work it out. Hit play to check your work. So if it's $2.50 per pretzel and it's 75 pretzels, I would multiply, right? $2.50 per pretzel, he sells 75 pretzels, and I use my trusty calculator. And I got $187.50. That's how much money he would earn if he sold 75 pretzels. Awesome. Let's talk about another situation. Delany and her friends recently went to the community fair. They had to pay an entrance fee and then purchase 1 ticket for each ride. So they had to pay to get in and then pay a ticket per ride. They had to buy tickets. Dakota is going to the fair tomorrow and wants to know the cost of each ride ticket. But Delany and her friends didn't keep very good track of things. So Delany and her friends helped Dakota by writing down how much money they spent and the number of tickets they purchased. So Delany and her friends, so we got somebody who only did 2 tickets and it cost her $7.50. Somebody else did 4 ride tickets, but it cost her $9. Somebody else did 6 rides, but it cost her $10.50. And somebody else who did 11 rides, and it cost her $14.25. So I would start by finding the slope and see if you can figure out what does this table tell you about the cost to go to the fair and to ride the rides. Go ahead, hit pause, work this out, play with it a bit, and then hit play when you're ready to check your work. So I started off by finding the slope, right? I was like, all right, I'm going to find the slope, first thing. And again, you can pick any 2 points you like. Just because I'm lazy, I'm picking the top 2 points. Feels easiest. So I'll subtract my y's on top, 9 minus 7.5. Subtract my x's on the bottom, 4 minus 2. So again, use my trusty calculator. 9 minus 7.5 is 1.5. 4 minus 2 is 2. And if I divide, I get 1.5 divided by 2, which is 0.75. So it looks like ride tickets cost 75 cents each. So I know that the ride tickets are 75 cents each, but remember it costs money to get into the fair. So I'm going to do a little bit of math here, and I'm going to use this first one to help me out, right? She did 2 ride tickets. So if I did 2 times at 0.75, that's why I have a calculator, that's $1.50, right? So she only spent $1.50 on ride tickets. But she spent $7.50 total. So fine, that means if I do $7.50 and I subtract the $1.50 from the tickets, that's 50. Oh, sorry, that's a zero. Just kidding. 0 minus 0, 5 minus 5 is 0. And 7 minus 1 is 6. Oh, look at that. I'm going to erase this and you can see the pretty writing. Let's erase it off. And you can see that means that it costs $6 to get in. So 75 cents per ticket, $6 to get in. Cheaper than the boardwalk. So Dakota's got $20 to spend. How many ride tickets can she buy? Hit pause, write it down, figure it out. Hit play when you're ready to check your work. So I maybe worked this a little differently than you did. You probably took your $20, subtracted 6, divided by 75 cents, and figured out how many tickets you could buy, right? I did this a little bit differently. I actually wrote a function. I was like, okay, well, f of x is the cost, right? The amount of dollars spent. I know that it's going to be 75 cents per ticket. And I know even if she bought no tickets at all, it's still going to cost her $6 just to get into the fair. So I actually used this function. And I thought, okay, well, when would this equal $20, right? She's got $20 to spend. So I just set it equal to $20, and then I did the math. I subtracted 6 from both sides. 20 minus 6 is, of course, 14. I then divided both sides by 0.75, and I got 18.6s going like forever and ever. The only thing is, Dakota can't buy part of a ticket, right? She either buys a ticket or she doesn't buy a ticket. She doesn't get to buy like a piece of a ticket. You either go on the ride or you don't go on the ride. So it looks like Dakota can only buy herself 18 ride tickets. One more. Can we do one more? The local pet store has a fish tank on display at the community fair. Darren is responsible for draining the tank at the end of the fair. The pet store manager provides him with this information from when they drained the tank at the end of the fair last year. So a quarter of an hour, half an hour, 3/4 of an hour, 1 hour, and this is how much water was in the tank. Wow, there's still a lot of water in the tank after an hour. That's a big fish tank. So my question is, how many gallons of water did the fish tank hold? Again, I would start by finding the slope. I know it sounds weird, but trust me, it's going to help. Start by finding the slope. Hit pause to write it out. Hit play when you're ready to check your work. So I busted out my slope formula. And again, you can pick any 2 points you like. I'm lazy, so I'm picking the top 2. I'm going to subtract my y values on top, 163 minus 169, and subtract my y values on the bottom, 1/2 minus 1/4. If you did them as decimals, that's okay too. I left them as fractions. So 163 minus 169 is -6. 1/2 minus 1/4 is 1/4. If you don't believe me, again, we could have made it into decimals. That's okay too. 0.5 minus 0.25 equals 0.25. And if you did -6 divided by 0.25, or in this case, I did -6 divided by 1/4. We don't like dividing with fractions, so we multiply by the reciprocal, so -6 times 4. And I get -24. So -24 gallons per hour. That's how long it's taking. That's how fast, I should say, it's draining the tank. So we're losing 24 gallons per hour out of this tank. So here's what I did. I know that every hour we've lost 24 gallons. So maybe the easiest way to do it is say, okay, 1 hour, 151. So you could be like, hey, 151. And in that 1 hour, we lost 24 gallons. So if I add that 24 gallons back in, I'm going to use my trusty calculator, 151 plus 24, just kidding, means that we started off with 175 gallons of water. It's not the only way to do it. You could have used any of these points. I just picked this one because one was easy, but you could have done the first one, right? You could have said, all right, 1/4 of -24 is -6. And 169 minus a negative 6 is a positive 6, and you get 175 gallons. So the fish tank holds 175 gallons of water. So here's the big question. When will the tank be empty? Hit pause, work it out, hit play when you're ready to check your work. So we've realized there's 175 gallons in that tank. If we're going to divide that by 24, right, because we're losing 24 gallons per hour, so 175 divided by 24 with my trusty calculator, ooh, that's not equals, we're going to say approximately 7.2916 is going forever and ever and ever. So about 7.29 hours. Yeah. Wow. Darren's going to be there all night. I'm sorry, Darren. That's not a great job, is it? If you really want to break it down, it's actually 7 hours, 17 minutes, and 30 seconds. Just saying. As always, guys, hope you found this helpful. I hope you found this useful. If you got questions or concerns, email me, come talk to me, office hours, lunch. You know the drill. And I'll see you guys later. Bye.